And this video is on the ideal gas law and problem solving using the ideal gas law. So up until this point, we've been talking about a variety of gas laws, Boyle's law, Charles' law, the combined gas law, a couple others. And so far, we have been able to solve for a few variables, and those few variables are temperature, pressure, and volume. Oops. So, oh goodness, I am a mess. So up until this point, we have not done any calculations that have allowed us to solve for the amount of gas in a container. So up till now, we've had no way to solve for the amount of gas, like the moles or the grams of gas that are present in a container. And so that's because we've never had a formula or a gas law that has given us a variable for moles or for grams. So that all changes with this new gas law, which is called the ideal gas law. This is probably the one that you're going to be seeing the most, and it looks like this. Okay, some of these variables you know what they are, some of them you don't, and so we will discuss that. So P, of course, is pressure. V is volume. T is temperature. Okay, and temperature is going to be measured in Kelvin. Volume is going to be measured in liters. Pressure, we'll kind of come back to this in just a second. So N is actually the variable that means moles, and of course they're measured in moles. And then R is a constant. It's called the ideal gas constant. Okay, and because it's a constant, that means it's going to be something that we can look up. It's going to be on your AP Chem formula sheet that's provided to you. There's no need to memorize the value of R, although you probably will accidentally from using it so much. But it is a constant. Now, because pressure comes in a variety of units, okay, and the two we see most often are atmospheres or kilopascals, there's actually going to be a few different values for R. Now, before I get into that, I want to talk about if we took this equation and solved it for R, we got R by itself. We'd have to divide by NT and divide by NT. And so what I'm left with is R equals PV over NT. So R has kind of some funky units because it's a pressure unit times a volume unit divided by moles times a temperature unit. So it's kind of an awkward unit for the ideal gas constant. So because we've already said pressure, we often see pressure in ATM or kPa, there's going to be two values of R, one that has a pressure in ATM and one that has a pressure in kPa. So the first value of R is 8.31, and that has a unit of kPa times liters over Kelvin times moles. And I know that unit to you is like, whoa. But again, you have to go back to thinking, well, it's a pressure times a volume over moles times temperature. Okay, and so that's why its unit is what it is. The second value of R is with a unit of ATM in place of kPa, and so that changes the number for R to 0.0821, and that is units of atmospheres times liter over Kelvin times mole. So again, these are the two values of R that we'll be working with the most, and we'll be talking about, when do I use which one, okay, in my practice. Okay, so that's pretty much it in terms of the background information on the ideal gas law. So we're going to do some problem solving. As always, you're welcome to stop and pause this video and try these problems without me. But of course, I will try them, or I will solve them with you. We're actually going to do number 2 first. And, okay. So, it says when the temperature of a rigid hollow sphere containing 685 liters, so I want to kind of make a note of what those are. That's a volume. Of helium is held at 621 Kelvin. That's a temperature. The pressure of the gas is this. How many moles of gas does the sphere contain? Okay, so again, if you don't like to underline and label them in your problem, then you've probably written them out to the side. This is kind of keeping track of your known values. We know the volume, we know the temperature, and we know the pressure. Oops. What we don't know is moles. That's in. And so obviously this problem is asking us to find moles. So I have the ideal gas law, PV equals nRT. And I want to find N. So I need N by itself. You'll never see me plug numbers into this formula before solving for the variable that I want. So I need N by itself. You can divide both sides by R times T. And I get N equals PV over RT. From here, it's just plugging in my numbers, checking out my units, and solving it. It's fairly simple. So I know my P, it's 1.89 times 10 to the third kPa. I know my volume is 685 liters. I'm going to skip R for just a second. I know my temperature is 621 Kelvin. Now, remember we have 2 values of R that we can use. One has units of kPa and one has units of ATM. So since in this problem I was given a pressure in units of kPa, I want to use the value for R that has kPa so that my units cancel. All right, so let's talk about canceling of the units. So kPa's cancel, liters cancel, kelvins cancel, and I'm left with moles, which surely makes sense because this problem asked me to find moles. So I plug this in on my calculator, making sure not to make a numerical error, and how many sig figs? Looks like 3. So I'm going to report this as 251 moles of helium. And that's my answer. Okay, so number 1. A deep underground cavern contains 2.24 times 10 to the 6th liters. Okay, so again, if we're identifying our variables, that's the volume of methane gas, CH4, at a pressure of 1.5 times 10 to the third kPa. So there's my pressure, and a temperature of 315 Kelvin. How many kilograms of CH4 does this represent? Okay, so I have a V. I have a P. I have a T. And, oh, shoot, I got ahead of myself. We know we're looking for, okay, here we go. We know we're looking for the kilograms of the gas. So this is a little bit different because we know that the ideal gas law has no variable to solve for kilograms. So we think about what possibly could I solve for to then take that quantity and turn it into kilograms. And so that the only variable that makes sense would be to solve for moles, because I know that I can take moles, change to grams, and then change to kilograms. So just like before, if we solve the ideal gas law for N, we get PV over RT. I plug everything in. My P is in kilopascals, so we're going to think about what value of R that we would like to use. And that would be the one that has kPa. And then my temperature of 315. All my units cancel except for moles, which of course should make sense to us. And I need to number crunch this, so give me just a second. And I'm not going to round significantly here because I'm not done. So I got something like, what's a huge number? I'll put it in scientific notation. 1.28336 times 10 to the 6. And that's moles of CH4. Okay, so I'm not done. Because I was asked for kilograms. So from here, of course, we can turn moles into grams using molar mass. And then, of course, we can turn grams into kilograms. The molar mass of CH4, let's see, 4 H's and 1 carbon. So 16.042. And that's it. I'm going to do my math. And let's see, sig figs should be 3. So to 3 sig figs, we get, let's see, 20,600 kilograms. Or, of course, you could do in scientific notation. Okay, it's a big amount of CH4. But it does make sense because this was a huge cavern, the volume was huge, and so we would expect a big number. Okay. And then the third one, a child's lungs can hold 2.2 liters, so that's a V. Oops. About how many grams of air? So grams is what I'm looking for. I have a volume. I have a pressure. And a body temperature of 37. So I know I'm going to change that. Let's see, that's 310 Kelvin. Okay, and then it says use the molar mass of 29 grams for air, which is about 20% oxygen and 80% nitrogen. Okay, so how many grams? Of course, same idea. I'm going to solve for moles. And then turn it into grams. So P was 102. V was 2.20. Again, I'm going to pick the R that has kPa. And everything cancels except for moles. And again, I have to do my math. We get something like, again, I'm not going to round here. Let's see, 108 or something like that. And they said use a molar mass of 29. So that's what I'm going to use. And let's see, sig figs should be 2 because of my temperature. So the 2 sig figs, 2.5 grams of air. It's a pretty small amount. So there you go. Real quick, I do want to take just a second to talk about why this 29. Okay, we know that air is a compound, so we're not used to seeing a molar mass for air. So they approximated, and what they did was they said, well, if air is 20% nitrogen, 20% oxygen, and that's oxygen, who's got a molar mass of 32 approximately, nitrogen, who's got a molar mass of 28 approximately, well, then the molar mass for air would be 20% of oxygen's mass added to 80% of nitrogen's mass, and to the nearest whole number, that's 29. So, we didn't have to calculate that or anything in this problem, but I thought it was interesting to talk about that's where they got that number from. Basically, it was a weighted average of oxygen and nitrogen's molar masses.